So, good evening, everyone. Welcome to the problem solving session 8 for the NPTEL course Unsaturated Soil Mechanics. And last week, we have discussed about partly about where there was one lecture about transient flows and how you can use finite difference method to numerically solve the Richard equations to find out the variation of volumetric water content or matrix action with time. In the next two lectures, we had discussed about the shear strength of unsaturated soils. Initially, the concept of shear strength of saturated soils or dry soils were discussed, and later on, the concept of effective stress parameter xi was introduced to define the shear stress of unsaturated soils. So, the questions today, you can see it on your screen. The same questions have also been added to the chat. And the first question that you see is we have already discussed this. Uh, it was to find out, write a code to compute the water content profile at certain times by solving the Richards equation using the finite difference method. So it is very similar to what the professor has taught, and but here now you have to apply the boundary conditions and the parameters are also given. So try to solve this. This will try, I mean, this has been already discussed, but just try to solve it yourself. Second part is using Hydros 1D software. A few weeks back, we had introduced this software, which is freely available software, and the same has been discussed in the lecture also. And using this software, compute the water content variation in 1 year in a 20-meter unsaturated zone, where top 5 meter is sand overlying 15 meter of sand, silt, and clay. So, so this will be actually make three cases. So you have three cases where first top 5 meter is sand and the bottom 5 meter is can be sand, silt, or clay. So you have three cases. You have default hydraulic models present in the Hydro software, so you can use those parameters and assume average monthly rainfall of your city. You can just Google it up, you will easily get it, and run it for 12 months. And you have to ensure that no ponding conditions occur. Ponding condition means that if you input what is the flow rate at the top as a boundary condition, then that for that flow rate, the pressure will be calculated. The pressure, if it is greater than zero, that means that the water is able to stand at the top of the soil. But generally, due to the slope of the surface, that water does not stand on the soil and it runs off. So then in the field, many a times, or most of the times, there is no ponding condition. So in order to simulate the same in the simulation also, what we can do is that we apply a flow condition based on the annual daily rainfall of your city, and then the software calculates what is the value of h for that q using the Darcy's equation. Now, if that H is greater than 0, the boundary condition is replaced by H equal to 0. That means a saturated condition, but there is no head. If that H is less than 0, then the uh, flow boundary condition is placed. So these are the two cases how we can how the using these two cases we can actually simulate that there is no ponding that is going to occur. And also it's written that also assume initial condition in top layer as 20% and equal to field capacity in lower layers. So how do you calculate the field capacity? So first of all, field capacity is that water content at which if you leave the soil as it is, it will roughly be equal to the same water content, and it will the water content will not change uh, due to gravity. So the way to calculate is there are many methods, but the way you can calculate is that you have to calculate uh, the water content at which the permeability roughly equals 10 to the power minus 9 meter per second. So you can find out what is the relationship of permeability and water content, and the water content at which the permeability is equal to 10 to the power minus 9 meter per second, that will be your field capacity. So you have to take that field capacity. Third question is that under the same external loading condition, which state, saturated or unsaturated, has a higher strength? What are the possible state variables that control changes in soil strength? Among the controlling variables, matrix suction, the effective stress parameter, and the suction stress, which one do you think will be more representative to describe the strength of unsaturated soil? And now question number 4 and 5 are basic direct shear tests and triaxial test data. And triaxial test has not been discussed. It will be discussed in the next lecture, but still you can give it a try because it is very similar to the concept of direct shear test. And you have based on this you have to plot some graphs. You have to find out what is the matrix section, what is the effective stress parameters, and that is all. So please give it a try. We will discuss the solution at uh, 8 10 p.m. 8:10 p.m. we'll discuss it. So yeah, you can try. So we'll see the solutions now. Uh, you can see this code we had already discussed. We have that divided the domain into 101 nodes. So each length of each node would be uh, 3 centimeters. And so you can see this length of each node is calculated here. That is total depth is 300 centimeters divided by 100. That would give 3 centimeters. And the time would be step would be 0.001 days. So it is important when you are using finite difference method. We know that if you are using explicit method, the error is of the order of delta t square. So you have to take a very, very small time step so that to ensure the accuracy. Then the final time step, final time till which the simulation will run is 20 days. And these are the time steps divided. Then the these are the parameters of Van Genischen parameters. And then we have initialized different state variables. H is your matrix suction, Q is the flow, W is the volumetric water content, C is the soil moisture capacity, which is the slope of the SWCC curve, K is the permeability, and SE is the effective degree of saturation or the normalized water content. Now we have to give the flow rate at the top. So it is given as -1 centimeter per day for half of the time step as given in the question. The initial condition is taken as -100 centimeters, and the bottommost point. So here the uh, first row indicates the bottommost point, that is at 300 centimeter, which is at groundwater. So there the head would be equal to 0 because it is in saturated condition. But as we have discussed, the term C, soil moisture capacity, goes to 0 when the head becomes 0. So that leads, since it comes in the denominator, that leads to numerical instability. And that is why head is equal to -2 is chosen to avoid that numerical instability. Then we calculate for the given initial condition, we calculate what are the other state parameters based on the Van Genischen equation. This function is defined elsewhere. So if we have, just give me a second. So if we have So if we have uh, these parameters, we will use this function to calculate the rest of the parameters. And then we have simply used the finite difference scheme. This is the Darcy's equation. K has been calculated. K is the average of the permeability at two different nodes. And this is the first order approximation is used, dou H by dou Z plus 1. So first order approximation is used to calculate this value. And the initial flow rate has been calculated based on the initial head distribution and the initial permeability. And the boundary condition has also been applied. The bottom boundary condition of head equals to 0, which is replaced by -2, and the top boundary condition is applied. Then the calculation. This is our equation of flow, which is the combination of which is the mass balance equation. So using this, we have calculated what is the pressure for different time steps. This for loop runs for different time steps. After that, the same procedure is repeated again. We calculate other state parameters and the material constants, and then we solve what for Q using the Darcy's law. And once we have that, we just have to plot it, and I can show you the result. So this will be the result. This is water content with time. So this blue line is at time t equal to 0. Then as there is rainfall, the water content increases at the top. This is the wetting front, and there is some capillary section also occurring. And in 10 days, it moves even further down. And in 15 days, it again starts decreasing because the flow rate at the top has stopped and the water is flowing under gravity. And then after 20 days. So let's get back to the next question. Next question is using Hydrus 1D compute the water content. So you can just put in the values and I'll just show you. So I hope you can see this simulation was run, and so you can see the different months. So this is the initial condition. Let me display it. So January, this water content is moving higher in sand, and now you can see there is an increase in water content. Uh, So you can see the water content is going down, and sand it's more, and currently it's flowing under gravity, but in June and July, in the months of monsoon, July and August, sorry, you can again see that the rain is coming. So that you will see in July. Yeah. So this is the rain coming from the top. And so this initial movement in the unsaturated zone is because of the water at the top. And you can see at the top there is a decrease in water content because of the evaporation taking place. So evaporation is modeled as a outflow from the system. So this is how you can solve. So this animation is not generated by MATLAB, sorry, Hydrus, but you can use MATLAB to generate this kind of animations. Uh, Next question is very simple. What are the possible states, variables that control changes, and which is the most important? So you know that the matrix suction and the net normal stress and the suction stress is important. So suction stress is the whole term, xi times the matrix suction. So you can say that the suction stress is more important than matrix suction or the effective stress parameters in itself, because uh, even if the water content is very low, even if the matrix suction is very high, the suction stress is going to be very low. And if the water content is very high, uh, even the effective stress parameter is high, but the matrix suction would be very low. So majorly it is defined by suction stress. So next question, we have already kind of solved this similar example in the class, where two tests are conducted initially at saturated condition to find out what is the value of C dash and phi dash. Once you know the value of C dash and phi dash, and you know that it does not change even in unsaturated condition, you can you can find out the value of xi for different degree of saturations and matrix suction, and then accordingly plot all the values. So these are the plots: effective stress parameters versus degree of saturation. We know that it increases. Then we have effective stress parameters with matrix suction versus degree of saturation. And so this is basically SWCC curve only. And then suction stress versus degree of saturation. So you can see that at lower degree of saturation, it kind of mimics the SWCC curve. Then some triaxial test results are given. I think triaxial tests will be covered in the next lecture, and since we have a tomorrow only, so we'll discuss this question tomorrow only. For now, you can give it a try, but we will discuss this problem tomorrow only. So that is all for today. I'll see you tomorrow on Saturday, 3 to 5 p.m. Yeah, thank you very much.